Last year at CPPCon, I gave this talk where I showed this amazing piece of code that calculates module 7 with just 2 assembly instructions, as opposed to 12 needed by the modules operator. I explained where this magic number comes from. Here it's in binary, and it has to do with the reciprocal of 7. So tonight, I'm going to show you even more amazing magic around reciprocals. First, how to calculate the reciprocal of a number without doing any division, by finding the root of a function using the Newton-Raphson algorithm. So the function is this one. Its only root is the reciprocal of d. That's the derivative, and this is the Newton-Raphson iteration, which simplifies to that expression, which contains no division. So let's implement this algorithm. So here are 2 pieces of code. Then, whenever code appears, Godbolt, the wizard, whispers spells from his corner, and you know what that means. So the code on the right is to calculate the reciprocal of 3 and works with doubles. The code on the left is to calculate the reciprocal of -3 and works with unsigned integer. It looks rubbish, doesn't it? Let's see how it goes. So those are the initial values, and they get updated to these, and these. And as you can see, x is fast approaching 1/3. And why? It's just drifting away. At the next iteration, x does convert to 1/3 up to the precisions of doubles, of course. And y looks like there is a big bug here because the value was not even updated from the previous iteration. But actually, this is expected. There is no bug here. Oh, good shot, Matt. So what do I mean by this is expected? Am I suggesting that this big magic number here is the reciprocal of -3? If so, then its negation should be the reciprocal of 3, right? So let's hold on for a minute and see a division by 3 in the context of pointer arithmetics. So this code calculates the difference between 2 pointers pointing to objects of size 3. So behind the scenes, it calculates the difference in bytes and returns that difference divided by 3. So let's see how GCC and Clang perform that division. They multiply by the magic reciprocal. But how? Which magic is that? Fuck wizard, shouted the wizard. So, but seriously, can we make sense of this magic? Let's try. So these 2 pieces of code, they operate in 2 different words. And for this particular example, the fine line dividing these 2 words is actually not a line, it's a dot. It's the binary dot. That's why I'm going to show you again the values of x and y, but this time in binary. And I'm also going to show you the value for the arrow functions, which somehow I expect to converge to 0. So those are the initial values, and pay attention to x and y. The pattern is pretty clear. At each iteration, we are doubling the number of correct bits. But more importantly is what happens to u and v. At each iteration, we are doubling the number of zeros next to the binary dot. For u, this means we are pushing the 1 away to the right, making u closer and closer to 0. And that's what convergent means, right? But for the code on the left, for v, we are pushing the 1 to the left, so v is getting larger and larger. It's not getting any closer to 0, but instead is getting divisible by larger and larger powers of 2. And the only number that is divisible by all powers of 2 is 0. So in that sense, v is converging, is getting closer to 0. Ad infinitum, they get there. So the word on the right is the familiar word of real numbers. And the word on the left is the beautiful word of 2-adic numbers from number theory. And as you know, doubles, they provide a flawed or truncated model for real numbers, right? And similarly, what I'm illustrating here is that in some circumstances, unsigned integers, they also provide a truncated, flawed model for the 2-adic numbers. That's magic. But bonus point, these 2 pieces of code, they were calculating partial sums for these 2 power series that you see on the screen. And the derivation for the limits that you see here, they make perfect sense in the respective word. But if you cross the line, they are rubbish. Fork wizard. Thank you, Max. Thank you.
Oh, 2 seconds to spare. Amazing. Thank you very much, Cassio.